Good afternoon, everyone. I've been getting a lot of emails lately from the Writing Center. I think probably my spam filter is going to be totally full at some point, but I'm checking all of them, and when I receive the messages, I'm updating the grade. So within just probably an hour or two of your appointment, you should see the points online for doing the appointment. The deadline for that is 5 o'clock on Sunday. And yes, question? Well, then I didn't get an email from them. You should go back over and talk to the person you had the appointment with and ask them to send me the email. Because by now I should have entered it in if you had the appointment then. Okay. The next homework assignment is due on Sunday. We're going to do 2 sets of calculations today that will help you solve that assignment. And then the big event next week is our exam. We'll have it during our normal class time. And you can prepare a 1-page equation sheet using both the front and back is okay. You can put anything you want on the equation sheet. It can be formulas. It can be procedures, encouraging notes from your mom and dad. Whatever you need to get you through the exam, you can put it onto the equation sheet, okay? There will be 2 parts for that exam. At first, it will be concept questions, and you have to put the formula sheet away for the concept questions. Those are just your own understanding. But then on the problem solving, that's when you can use the formula sheet that you've prepared. All right. We're going to continue talking about secondary treatment today. Specifically, we'll do some calculations related to oxygen demand, and then talk about one of my favorite things, which is attached growth. We have to deliver oxygen to the bacteria. Why? So that they can eat. They need 2 things. They need food and they need oxygen and some place to live. We're providing a habitat for these bacteria. You could look at it that way. The habitat is the aeration basin, and for them to be happy, they need to have plenty of oxygen. One of our ways to do that is with a surface aerator, and that's what this picture is showing. Surface aerator takes oxygen from the surface and just basically circulates it down with a big fan. It looks very similar to a fan that you'd maybe have in a room to get the air moving around. And last time I was there, which was 2008, the wastewater treatment plant here at University City had a surface aerator, similar to this. And so there's wastewater splashing all over the place. You don't want to get too close. When we'll take the tour, then you'll definitely understand why. Surface aerators are a little bit less efficient than diffusers. With diffusers, instead of adding the air at the surface, what you do is you put some sort of an air stone underground, not underground, under the water surface, and with very small pore size on the diffuser, you're allowing the oxygen to sort of bubble upwards. And it's naturally lifting the water as the bubbles go up, and it causes sort of a recirculation pattern inside the aerator. And sometimes they'll use pure oxygen to do the aeration, and the advantage of adding pure oxygen instead of just normal air from the atmosphere is that then you have a higher fraction of oxygen that's getting into the wastewater. Mm-hmm.
First picture, we have that.
Surface aerator?
Yes. Does it not serve the bacteria like won't allow them to eat as fast because
The bacteria in the aeration basin, there's probably an upper limit. Like if they were colliding so hard that it was shearing their cell walls, they wouldn't be able to eat. But the amount of mixing that it does in here, it doesn't interfere with their ability to eat. Yeah. The bacteria aren't like us. We wouldn't have much of an appetite if we were banging around all over the place. But I guess probably because they're small, it doesn't affect the bacteria. Here is a look at a diffuser assembly under that would normally be covered with water. They've drained this for maintenance. And you can see that each one of these little circles is a membrane with lots of little holes in it. So it's sort of like a balloon that has small holes in it, and so that fine bubbles rise upwards through the water. The smaller the bubble, the better it is for air transfer. So think about, I'm drawing on the board here, water, and if we had an aerator with big holes. If it has big holes in it, then the bubbles themselves will be large. If the bubble is big, it can float to the surface very quickly. It's kind of similar to when we were talking about particles and how when they're settling downward, a big particle can settle fast through water and a small particle settles slowly. Because the larger it is, then the settling velocity is larger because the ratio of drag to weight is different. Whereas a very small particle like this is going to have a lot of drag as it moves downward through the water. So these bubbles are going up. Big bubbles would move quickly, and that's not what we want. We want there to be a lot of contact between the air and the water because we're trying to get the oxygen from the air into solution. Because the bubbles don't stick their head, the bacteria aren't breathing the gaseous oxygen. They are consuming dissolved oxygen. So we want as much dissolved oxygen as we can.
So why don't you just close the container from the top so that oxygen stays within the dump?
If they're using purified oxygen, they might enclose it. But if it is just atmospheric concentrations of oxygen, then there's no advantage to enclosing the aerator, other than reducing smell. Sometimes in an urban area, they might enclose the entire wastewater treatment process, but putting a roof over this wouldn't enhance the oxygen transfer. But small bubbles will. So the big bubbles are bad because they just float to the top really quickly and the oxygen can't get into the water. But if you have tiny little bubbles, they float to the surface really slow, and because they're so small, it's easy for the oxygen to get into the liquid. So that's what we're trying to achieve with these diffusers, is the smallest bubble size that we can get. The problem is that membranes that give you a small bubble size require a lot of maintenance. And so it's like a balancing act. The water inside the aeration basin has to be between 0.5 to 2 milligrams per liter, and it depends on what species of microorganisms are in the aeration basin. What's there sort of governs what you need as your absolute minimum. Higher is better, though. As a rule of thumb, each meter of wastewater requires about 8 cubic meters of air to be provided. And electricity costs, I showed you a figure before of where, what's the cost of treating wastewater. Electricity is one of the biggest costs, and it's because of this. Providing loads and loads of air into the aeration basin requires really big fans and blowers, and that's where a lot of the electrical consumption comes from. Here's a formula that we're going to use in today's in-class exercise that tells us the mass in terms of kilograms per day of oxygen that's required. Now, this formula doesn't take transfer efficiency into account. This is just talking about actually how much mass of oxygen the bacteria themselves are breathing. So we have to add a lot more oxygen because most of the oxygen we add is going to float to the surface and then go out into the air. And so this formula just tells us how much is being consumed by the microorganisms that are in solution. And you'll notice that it depends on the flow rate. And of course that makes sense because the more water you're treating, the more oxygen they'll require. And then the difference in S. Why do you think this parameter is in the formula when we're calculating how much oxygen is required? Difference between the inflow BOD and the BOD of the effluent from the aeration basin. How much food they ate. Yeah, if we were going to put a name on what's in the brackets there, we'd call that how much food they ate. And how much food they ate has a direct one-to-one correlation between how much oxygen they need. Because remember the way we measure their food? We measure their food in terms of oxygen demand. BOD, biochemical oxygen demand. And so if we're measuring how much they ate in terms of oxygen, it becomes very easy for us to calculate the oxygen they require. Here's the conversion factor between grams and kilograms, and we can express these concentrations in terms of grams per cubic meter. Grams per cubic meter is the same as milligrams per liter. F is a fraction between the 5-day BOD and the ultimate BOD. And I hope you remember a figure that we saw that was showing over time how much oxygen the bacteria need to break down waste. And what it shows is that if you give them a really long time, eventually they'll require this much oxygen. But after only 5 days, maybe they're not quite there yet. They haven't finished the meal, so to speak. And so if this is our 5-day BOD, S0, then the ultimate BOD is what we kind of need to keep track of when we're calculating the mass. And so this F corrects for the fact that our substrate concentrations are in a 5-day basis rather than an ultimate basis. And finally, we subtract the mass of sludge solids that are produced because there's less of an oxygen requirement when they're adding new cell mass than when they're actually doing respiration. The food that they're eating can go one of two places. It can go into additional body mass or the activities that they're doing, or respiration. And respiration requires the oxygen. And so this corrects for that on the basis of the mass of sludge that's produced each day. So let's give that a shot. You've got in-class exercise 29 there. We're sort of a continuation of a previous example where we've got the same flow rate that we had in class 28's example, the same inflow concentration, 84 milligrams per cubic meter of BOD coming in. 11.1 was the allowable concentration going out, dissolved BOD. And we had calculated in that previous example a sludge rate of 436 kilograms per day. So in step A and B, what you're going to do is first of all require the mass of oxygen required, and then in part B, we'll convert that to a volume basis, knowing the density of the air and the purity of oxygen inside of air. All right, so here's the direction we need to head in for part A. Just as a reminder, S0 is the 5-day expression of BOD. L0 is the ultimate BOD. So we can calculate F from that. And here's how much oxygen is required on a mass basis per day. Any questions about this part so far? All right. Now over here to what I told you from the board. If we have 1.185 kilograms of air per cubic meter of air, then we can multiply like this. And then that gives us 0.275 kilograms of oxygen for every cubic meter of air. Anybody know what air mostly is? Nitrogen. Air is about, 75% nitrogen, 23% oxygen, and the rest of it argon, helium, hydrogen, and so on. Okay, so the final thing is if we're accounting for how much oxygen is in air, this tells us the volume of air that's required. About 2780 cubic meters of air is required. But that assumes perfect transfer. Remember, what we know is aeration. Most of the air that's delivered under the surface is going to make it to the surface and bubble out. And so this is how much volume of air you'd have to add if all of it was being dissolved. So the reason why we say 8-to-1 as a rule of thumb is because we know that most of the air isn't going to be dissolved. Most of it escapes. But strictly speaking, this is the mass and corresponding volume of air that would be required if it was 100% transfer efficiency. All right, are there questions on this example?
So what's 764?
What is 764? Oh, this was part A. So it's the mass of oxygen per day that's required. Other questions? All right. We're done talking about activated sludge for now, and we're going to move on to something different. Activated sludge is a kind of treatment that's called suspended growth. The bacteria are floating around inside of the water. So they're suspended in solution, and what do they do while they're suspended? They're eating food and breathing oxygen. So they consume substrate and they require oxygen from dissolved oxygen. The next kind of secondary treatment we're going to talk about is called fixed growth. And instead of the bacteria floating around in a tank, the bacteria are living somewhere on a solid surface. And so we'll pour the water on top of the bacteria instead of having them float in it. So it's a little bit different. The difference, you know, on exams I like to ask you questions like, tell me the difference between one thing and another thing. And that doesn't mean define each of them. That means tell me how they're different. So the difference between suspended growth and fixed growth, the first thing is where they live. The fixed growth is living attached on something. They're not floating around in a tank. They're stuck on a surface. They're still consuming substrate, meaning they still break down BOD. They're eating food. They're still breathing oxygen. But things are a little different because of where they live. Here's a picture of water being sprayed onto rocks. And we can get bacteria to live on rocks if we spray wastewater on the rocks. And as they live there, they consume the BOD. So let's talk about that in more detail. But first, we'll talk about something known as a rotating biological contactor. This is the last question on your homework assignment. It's about RBCs, as they're called. It's abbreviated. This is a building that's full of these discs that circulate around. They're attached to a motor, and they circle around. They dip into the water for part of the time, and they're above the water surface. So it's like a swimming pool full of wastewater, and these discs are partly submerged in the big tank of wastewater. And the reason for that is that as they're submerged, the bacteria that's on the surface dips into the water, grabs some food, and then when the bacteria is above the water line, it's exposed to oxygen. And so it's constantly, think about a bacteria that's living right here. This is the habitat of the bacteria, is on the surface of this plate, and the plate sometimes is going under the water, and sometimes it's above the water. And so it's cycling between access to food, access to oxygen. And of course there's also some dissolved oxygen in the water. The movement of these discs introduces some mixing and helps with aeration. Yeah.
The bacteria is fixed on the...
Yeah, it's like a film, like a scum.
Does not like get off the film?
Sometimes it does, yes. Like the film gets thicker and thicker as the bacteria grow. And so sometimes the film will get so thick that the movement makes it fall off into the water. But that's what we want. That's good, because remember, the whole point of secondary treatment is to turn a dissolved waste, BOD that's dissolved. We can't settle that. Even if we put it in a clarifier, it's dissolved, so it's not going to settle to the bottom. But the scum that falls off, that will settle to the bottom in the secondary clarifier. And so you're absolutely right that eventually it's the bacterial layer is going to get thicker and thicker and thicker until it falls off, and that gets entrained in the water and settled in the clarifier. So this is just a different way of bringing the waste into contact with the bacteria. Mm-hmm.
Don't they only take dissolved oxygen?
So you're wondering, how are they breathing oxygen when it's up in the air? The reason that they're able to do that is because there's still a layer of water on top of the bacteria. Like, it's not getting totally dry. If this was moving too slow, it would kill the bacteria. But it's only above the water line for maybe 1 minute. And so there's still, the scum layer is naturally wet, and there's a very thin layer of water covering it. And so since the the film of water is so thin, it's very easy for the oxygen to penetrate, but the bacteria doesn't get dried out. That's a good question. I'm glad you asked it.
So,
Mhm.
what is the trend between the terms horizontally and vertically?
There's a lot of different configurations of this. I mean, it's not always a rotating thing. There's a lot of different patented methods. People are always thinking about how can we get bacteria in contact with the substrate, and so there's possible it could be horizontal instead of rotating. Here's another way of doing it. The advantage of this is it can be very, very eco-friendly. You need hardly any electricity at all in some cases to have a trickling filter. With the RBC, you don't need a lot because you don't have to have big blowers of oxygen. Remember, with the diffuser, a lot of the electrical costs are forcing air underwater. Here, you don't have to do that. You just have to have a small motor to rotate these contactors. Well, it's even better with a trickling filter because there's an arm. This is a cross-sectional view. The media is rocks, and this arm is rotating around in circles, spraying wastewater onto the rocks, but the rotation of the arm can be powered by the jets of the water that's coming out. Here's a picture that's showing sort of an isometric view of it here. So here's an arm that's rotating around, and sometimes they'll put a motor on the center just in case the water flow rate's not enough to power it. But you'd have rocks here that have a thin layer of bacteria living on the surface of the rocks. So when the water is sprayed, the bacteria are reaching into that water and taking out their food. Mm-hmm. The volume that you can treat? How do you figure? Oh, because it seems like very little water. Yeah. Well, the volume of this trickling filter has to be bigger than the volume of a activated sludge basin would be. So it requires some more land area. And the other issue is that the water passes very quickly through the media. Let's go back to here. As soon as the water comes in, it's moving very fast to the bottom. And so the bacteria doesn't have very much time to reach out and grab the food. It has to grab it quickly. So each time the water comes down, it's only removing just a little bit of BOD. So we have to recirculate it several times. And that's how we kind of control the liquid contact time, because otherwise the water would go from the top to the bottom in maybe just a few seconds. And that's not enough contact time between the bacteria and the liquid.
So would you add dissolved oxygen to that water itself?
No. What we'd have is at the bottom of the rocks, we'd have sort of like a stand that the rocks are supported on, like a rack, maybe a table with holes in it, and the air can naturally diffuse upwards. So this isn't fully saturated with water. It's mostly air inside of here, and so air is kind of breathing in from below and from the top, and so the water is just passing through and it's coating the rocks, it's getting them wet, but the voids between rocks is mostly air. Okay, here's a process view, and it shows, you know, we have our pre-treatment stuff like the bar rack and the grit chamber. We have our primary treatment, which is just to get grease out and settleable solids. But now, coming out of primary treatment, there's still loads of dissolved BOD. And the only way we can get that dissolved BOD is by growing something, growing the bacteria. And then we can settle that in a clarifier later on. So this trickling filter, you can see, is having a recycle that allows us to increase the liquid contact time with the rocks. If we didn't have recycle, then the water is just going through the rocks too quickly to remove much BOD. But if it's only 1 minute and we recycle 20 times, then that's effectively 20 minutes of contact. And so you can get the idea of why the recycle is important.
Sir, why doesn't the recycling get right after you?
It can, except for that, remember there's the scum layer sometimes breaks off, And so if we recycled from here, then we'd be recycling some of the solids that are breaking off. When the scum layer gets too thick, it's called sloughing. And like think about a rock that's covered in slime, slimy bacteria. When it gets really, really thick, the water sprays it, and then all of that slime layer falls off. So if we have the recycling from after the secondary clarifier, then what we're taking back to the head end is more water and less of that sloughed layer. So you've seen the picture. Here's another one. They can really be big fields. Sometimes they use rock, but more and more it's becoming common, instead of using rock, to use synthetic media, like little plastic pellets. What do you think would be the advantage of using plastic pellets like this instead of rocks? Yeah? Precisely. Yeah, you can increase the surface area. And why is that important? More contact between the bacteria and the water. This is all about getting the bacteria a surface to grow on. And so if you use large stones, the surface area of that stone is much less than if you have small media that has holes drilled in it. Then everything we want to do is maximize the surface area. And the other advantage is it's quite light. You know, those heavy rocks, we can only have a pile of maybe 3 meters of rocks before the support structure really has to be enormous. But if it's a pile of plastic pellets, we can maybe make it 10 meters tall, and still it's going to be very light at the bottom. Yeah. It can be used in sunny places, but algae can grow. And if there's algae that clog the top layer of it, if the algae grows so thick, then the water can't get through. And so sometimes it's important to have control of the algae. You know, sometimes it'll work in sunny places. Usually the problem isn't that it's too warm and sunny, but usually the problem is this doesn't work super well in really cold climates, because if the air is circulating through the rock filter, it loses the heat very quickly. And remember, bacteria they operate slowly in the cold. So usually low temperatures is more of an issue than high temperatures. This could be put inside of the trickling filter instead of rocks. So why would this be a good substitute for the rocks? Same reason. Maximize surface area. Here is another configuration of it where they would have hanging plastic sheets, kind of like a garbage bag draped downward. And so at the top, they're spraying water over those plastic sheets, and the plastic sheets are just an area for the bacteria to grow. You can see this is showing a blower. If you have very, very densely packed media, then sometimes the air can't naturally circulate through very well. And so just to provide an abundance of oxygen, you'd need to force feed air into the bottom of the trickling filter. But that's not always the case. So the way this works is that scum is growing on the filter media. The wastewater that's getting through the arm, it's rotating around in a circle, and it's occasionally wetting that surface. And it's a cycle of wet and dry. And it doesn't get all the way dry. It doesn't totally dry out the bacteria because they die, but it's a time when the water layer on the top of the media becomes very thin, and that encourages oxygen transfer. Now, calling this a filter is a little bit of a misnomer, because it's not actually straining that happens in the same way that a sand filter, remember what the mechanism in a sand filter was: impaction and adhesion. But we still call it a filter, even though it's not really straining. Here, it's not filtering out a suspended particle, it's just a location for dissolved BOD to be removed. Those slime layer eventually gets so thick that it sloughs, which means it falls off, and then it's removed in the clarifier. So this works great when it's appropriate. And I've actually been to a facility that was using trickling filters. It was in Utah, and it was just a beautiful thing. It worked perfect. The water clarity coming out of it was very clear. In fact, they took water from their secondary treatment and they fill a fish tank with it. It was clear enough that the fish seemed perfectly happy in their secondary effluent. If you have a really high concentration of BOD, then it may not work because the slime grows so quickly that it can clog the filter media. And so the sloughing happens too fast and the water can't pass through. And then the other issue is sometimes the oxygen doesn't get through the voids. If it's really high surface area, you'd have to use a blower. And then sometimes if it's cold weather, these cool off a lot more quickly than activated sludge does because of the contact with the air. We won't go into too much detail looking at the specific design parameters, but these are some of the rules of thumb that are used for designing trickling filters. Trickling filters are designed with empirical equations. The difference between an empirical equation and a fundamental equation is that an empirical equation is just based on observation. You know, it's curve fitting where you've observed data and you've observed the effect of changing some parameter in that data. And so recirculation is one of the main parameters that we have to go through in designing a trickling filter, because once you build it, it's about the only thing you get to control is how much of the water goes out versus how much of the water is recirculated back to the top. The reason why we do recirculation, as we've said, is to have a increased contact time as the water trickles downward, and it also, in low flow rate times, helps you from having the problem of if there's too little water, then the filter media could dry out. So recirculating the water over and over during the nighttime periods prevents the clogging that would happen if the filter dried and all the bacteria die. No, the recirculation happens all the time, but you'd increase recirculation at night. So this ratio, Q sub R to Q, would vary during the day. During the day, your recirculation ratio would be lower than at night. At night, you'd have a lot of recirculation, just because there's not as much wastewater coming through. Sometimes you'll have a two-stage filter. And what this is showing is, first of all, it's operating in parallel. The water that comes is split between a primary trickling filter, and then there's a clarifier, and then it goes to a secondary trickling filter that's used just as a polishing stage to bring the BOD concentration down even more. And so there's recirculation going on here. There can be recirculation on the second downstream trickling filter. This diagram is showing just a one-time pass as it's going through. The advantage of having different stages like this is that different species of bacteria will grow in each of the filters, and so that can allow you to achieve nutrient removal, like getting rid of excess phosphorus and nitrogen more effectively. All right, so we need to get into the design equations because you're going to do a homework problem related to this, and I want to show you some of the calculations. These are the empirical equations that you use. Take a note of the units for each of these. Flow rate is in terms of cubic meters per second in these formulas. Concentrations are milligrams per liter. So what I'd like to show you is an example where we have a two-stage filter, and we want to find out what's the concentration of BOD coming out of this filter in the discharge. So we know the volume of each filter because the diameter is given and the height, so we can calculate that. Here's the liquid flow rate of wastewater, the recirculation flow rate, and we know the inflow BOD is 160. Temperature is 17 degrees. So we're going to correct for the temperature because these design equations are assuming 20 degrees Celsius temperatures. And so when that's not the case, you have to correct for the actual temperature that's known. All right, so I would suggest you take good notes as I go through these calculations. That'll help you out on the homework problem if you've got the notes. Okay, so We're going to start off by calculating the cross-sectional area for a 17-meter diameter filter. The cross-section of each is going to be 226.98 square meters. Okay, and the height we know is 2.5 meters, or h equals 2.5. The volume will be 226.98 times 2.5, 567.4. Any questions so far? Okay. We'll go in order. We need to calculate R. So R is the ratio of the flow rates, 0.017361. Okay, so if we calculate the ratio, it's 2.5. The ratio, that 2.5 means that for every liter of water that goes out, we recirculate it 2.5 liters. Okay, with R, then we need to calculate F, this empirical factor F. Okay, so it's 1 plus R, so 1 plus 2.5 divided by 1 plus 0.1 times 2.5 squared. Okay, so that's going to be 3.5 divided by 1.5625. The F factor is 2.24. Now we calculated both of those just because they're going to go into these factors that tell us the efficiency of removal. E means efficiency, basically. Okay, so let's do stage 1. Stage 1 means the first filter that the water goes through. And we want to find the efficiency of stage 1 using this empirical factor. Put in the flow rates. Put in the volume, and then the factor for F. We have to take that to the 1/2 power, because that's in the formula there. So the efficiency for these conditions would be 0.8914. That means this is going to be removing 89.14% of the BOD. But that would be if it was at 20 degrees Celsius. This water is at 17 degrees Celsius. So will it remove more or will it remove less? It's going to remove less because the bacteria aren't as happy as they would be in warm weather. So we need to correct for the temperature. So the efficiency for stage 1 at 17 degrees is this first factor, 0.8914, multiplied by the temperature correction, 1.035 to the power of 17 minus 20. So it's to the -3 power. And when we do that, it's 0.8040. So what that means is that since the water is colder, it doesn't remove 89% of the BOD. It's only removing 80% of the BOD. So the concentration coming out of stage 1, the effluent concentration coming out of stage 1 will be 1 minus E1 at 17 degrees times the concentration in. And the inflow concentration was that 160. So 1 minus 0.804 times 160 milligrams per liter means that coming out of the first stage, the concentration of BOD is 31.36 milligrams per liter. Okay. We're running very low on time, so let me see. What I'll do is I'll post the PDF of the rest of this solution online. I'll put it into the other items folder online so that you can take a look at this example as you're working through the homework assignment. All right, that's it for today. Hope you have a good weekend, and I'll see you on Sunday.